Okay, hello everybody. So in this video, we'll look at small signal models for MOSFETs. Okay, so in our previous class, we saw the input-output characteristics or the voltage transfer characteristics of this particular circuit. Okay, and about VGS was supposed to be our input, and we're looking at the output at the drain of the MOSFET. This is the source, this is the gate, this is a power supply and RDD. Okay, so when you plot VO versus VGS, the plot looks something like this, that and this, where the x-axis is VGS, y-axis is output. So in this region, the transistor is in cutoff here, and this voltage was VDD. This region, the transistor is in saturation, and in this region, the transistor, and in this case the MOSFET, is in triode. Okay, and this was the voltage transfer characteristics of this circuit. What we talked about of making an amplifier out of this is we said, okay, we will look at the slope of this curve at each point, and we'll choose a point where the slope of the tangent is equal, the magnitude of that is equal to the gain we want. So we'll fix our DC point over there, and we will change our AC input. So that means we'll superimpose our AC input on VGS, such that if my VGS changes by small amounts, my VO changes by huge amounts. And the proportion by which my output relates to the input changes is equal to the tangent, or the slope of the tangent at that point. Okay, so and then at the output, if you're only looking at the changes in the output, that will be our AC output, and which is an amplified version of my input. So that was our basic philosophy of making amplifiers with transistors, right? And basically by approximating this curve around a point as a straight line. And how good our approximation is, that's what dictates how linear our amplification is. Okay. All right. So now what I'm going to do is I want to try and model um, the behavior of the transistor when the input is changing by small amounts, right? Ultimately, I want to replace this with the circuit elements, which with all the components in there, which are from our circuits 1 class. Okay, so let's do that. So now I know if I want to make an amplifier, I want to place the transistor or the MOSFET in saturation region, and in saturation, I have my saturation equation as ID is equal to half Kn VGS minus VTN squared. This is my saturation equation. This is VGS. Okay, so I want to see how my ID changes for small changes in VDS. So in order to do that, I will differentiate ID with VGS and say because now the derivative will be equal to the slope of the tangent, and say that is the gain at a particular VGS. Okay, so let's do this. If I differentiate ID with VGS, I get half times Kn times 2 times VGS minus VTN. Okay, and this is nothing but Kn VOV. Right. So now the approximation here is we are saying that the derivative is approximately equal to small changes in the current divided by small changes in my input voltage. Okay, so since these are small changes, I will call this the AC current through the drain, and so small changes in my input, I will call this my input voltage, input AC voltage. Okay, so now this implies my ID is equal to Kn VOV times Vi, which is I'll call this Kn VOV term as Gm, and this will be equal to Gm Vi. Okay, so now what is so Gm is basically the transconductance. So it's a conductance because it's a proportionality constant before voltage to convert into current, right? So voltage is resistance times current, and current is conductance times voltage. Now, the reason it's called transconductance is because it converts input voltage into output current. So it's a transconductance amplifier. Okay. So if I want to draw a model for this, then so note first that for my MOSFET, this is the source, the drain, and the gate. The current going into the gate is always zero, at least for the frequencies we are concerned about. So since the current going into the gate is zero, so this arises because there is an insulator between the gate and the remaining of the MOSFET. So that the insulator actually causes a huge amount of huge amount of resistance, and almost no current goes into the gate. Okay, so we'll, for all our purposes, we'll assume that always the current going into the gate is zero. Okay, so that means my input impedance is infinite, which is good. So if I want to draw a model for this, at the input side, I have my input impedance is infinite, so I'll just keep it open. Okay, and then I'm applying VI over here. Note that this VI means changes in VGS. Okay, and at the output, I have basically a current which does not depend on output voltage. It only depends on input voltage, right? So you can depict this as a current source. Okay, and this is basically source, and this is GMVI, right? Because current at this is the drain, this is the gate, this is the source, and the current going into the drain is equal to GM times the input voltage. Okay, so this will be our small signal model for our MOSFET. Okay, and we'll call this model specifically the pi model. It's called pi because the word pi derives from the equivalent model for transistors, for BJTs. For BJTs, there's also another resistance here, and when you actually draw that, this looks like an inverted pi, and that's where the name pi comes from. But for MOSFETs, this is not included because the input resistance is infinite, so we just open it. Okay, but we still call it the pi model. Now, this is a small signal model for my MOSFET, right? So if you see, it's just this is just open, and there's only one voltage dependent current source, right? And this we can deal with, right, using circuits 1 principles. So now next what we're going to do is use this circuit model for our MOSFET and derive the gain equation for this particular circuit here. Now note in here, even though we are replacing the transistor with a simple circuit model, now this circuit is a linear circuit, right? The input-output relationship is linear. But you have to remember that GM actually depends on VGS, right? So if my DC bias point changes, GM changes. So that means we'll have a different model for the MOSFET as for different DC biases. But once a DC bias voltage is fixed, then the model is fixed. Okay, so that's why it's not really a linear circuit, because you cannot replace the MOSFET with a linear circuit. But if you say, okay, if you fix the DC voltage, then the MOSFET approximately behaves like this for AC signals, right? If they're small enough, right? Because remember, this approximation is good only when these changes are small. Okay. All right. So now what we're going to do is analyze this circuit. So I'm going to first replicate the same circuit here. Page number 2. This is RD. Okay, and this is VGS. And I'm looking at the output here. Drain, source, gate. Okay, so the first thing I'm going to do, and then basically I'm superimposing my input on VGS, VI, right? So the first thing I'm going to do is replace this MOSFET with its equivalent circuit model. So let's, I'm going to draw the box for now just to make, make things clear. But as we move on, we'll stop drawing these boxes. Okay, and I'm also only going to consider the AC component of the input, right? So I'm only going to draw AC signals here. This is VI. And I know at the output, I have an AC current source, which is equal to GMVI. right? The actual current, the total current going into the drain will also depend on VGS, but here we're only concerned about the AC current. Okay. Now in this case, the source is grounded, so I'll ground this. This is the drain. This is the gate. Okay. Now, if you look at what else is connected to the drain, there is a resistance connected to VDD. Now, since VDD is constant, that means this voltage is not changing. As long as AC is concerned, this point is ground because the voltage here is not changing. So the AC voltage here is 0. So what I have here is then RD connected to ground. Okay, and this one is my VO, right? Now VO is the changes in the output because this is only the small signal model. Okay, so okay, so now I want to calculate, what I want to calculate is the AC gain, which is VO divided by VI, which is changes in voltage divided by changes in current. Okay, all right, so that means okay, so this will be, let's first okay, so the voltage drop across RD is VO minus 0, which will be equal to, let's say the current here is I in this direction, that will be I times RD. But if you see the current in this direction is I, and then the current in here in this direction is GMVI, that means this will be equal to negative GMVI RD. So this implies VO over VI will be equal to negative GMRD, and this is our gain. Let me just call A. Okay, so this is my gain A, negative GMRD. So the magnitude of gain is GM times RD. Okay, so that's our basic amplifier, and the gain is GMRD. So now remember, GM depends on your DC voltage, right? So GM is KN VOV times RD. So if you change your DC biasing point, you change GM, and that's how you change your gain. And you can also see if for a higher DC bias voltage, you have a higher gain. Okay. So let's say, okay, and then one more thing I want to say here is, if you look at the circuit here, or this model, as long as AC is concerned, source is grounded. I mean, even in DC, source is grounded. So, and you're applying input at the gate, right? So you're applying input between gate and the source, this source, and you're looking at output between the drain, because the VO is the voltage of the drain, and you're looking at the output between the drain and the source, right? So input is between the gate and the source. The output is between the drain and the source. So what's common to input and output is the source, right? So this is why this is called the common source, sometimes just see as amplifier. Okay, so we've looked at our first configuration, which is a common source configuration. We looked at our first amplifier, the common source amplifier. Okay, so we'll stop this video here.